Good morning, guys. Today we're going to look at calculations and how to carry out a hand calc. Okay, so the equations that we're going to look for to do this are the equation to work out the actual flow from a sprinkler head, which is Q, which equals the flow from sprinkler head of the K factor of the head times the square root of the P, or pressure at the head. The other one is when we want to work out the minimum pressure at the head to achieve a flow for that head, it is P, which is the pressure at the head, divided Q, which is the flow required at the head, divided by the K factor and square root the total amount of that. And finally is the shortened version of the Hayes and Williams formula, where we're trying to work out the pressure loss through the pipe. So we've got the K factor of the pipe, which we get from TB 227 table 2, times the flow going through the pipe to the power 1.85, times the length of that pipe, including all the bends, elbows, valves, etc. Okay. So if we take a kind of version of the calculator here, what we'll have here is the square root button, which is the blue button circled here. Okay, the square button is here, the orange, and also you've got the K factor, which we're going to need this button here, and also the square to the power button, which is that one here. Now that might look slightly different in other calculators, but the times 10 generally works out the same. The square root button doesn't look much different. The square button is x2, and then the power button is square. Okay. So if we take a quick look at this then and do a quick Hayes and Williams formula. So if we've got the pressure, which is the pressure loss in bars, K is the K factor in the pipe. Okay, so we've got a table here showing some K factors of pipes. And the Q is the flow through the pipe, and L is the length of pipe work, including equivalent lengths, fittings and valves, etc, etc. Okay, so if we say what's the pressure loss through a 25 diameter pipe at 100 litres per minute, 5.5 metres long, what we'll find here is if we look at the table above, it tells me the K factor of the pipe at 5.11 times 10 to the minus 6. The flow of 100 litres per minute is in the question, and the length is also in the question here. So we come down, we then put that together in line, like we would do for the Hayes and Williams formula. So we've got the K factor here, times the flow to the power 1.85, times the length. Okay, now remember, it'll be 5.11, and then you press the green button here, times 10, and then type into your calculator, take away 6. You then hit the times button, and then type in 100, and then press either the x squared button or the square button, depending on the calculator you have. That then takes your cursor up into the power range. You type in 1.85 and then hit equals. Once you hit equals, you'll get a number of 0.02, etc, etc. You then times that by the length, and that gives you 5. Once you times that by the length, it gives you 0.1408 bar. Okay. Now remember, guys, accuracy is always to the millibar. So when you've got barrage, it's 0.123. So realistically, that pressure should be 0.141 bar. Okay. So if we take that into a a situation like this, now this is a ordinary hazard group 3 security office actually, with sidewall heads in it. Okay, now what we're going to look at is flow calculations here, because it's important. So when we've got two legs, so in this instance we've got the north leg and the south leg, okay, and what's going to happen is we're going to require more pressure at the north leg than we do in the south leg, and that's simply because we've got more pipe up here. More pipe equals more pressure loss, so the pressure required at this point here will need to be more to feed the three heads. Because that's shorter pipe, it'll be less pressure. Okay, Righty, so for instance, on here we've got 153.4 litres per minute going the north leg at 0.798. And then on the south leg, it's 152.08 at a pressure of 0.606. Remember, third decimal place. Now, the thing here is, what's going to happen is that pipework's not intelligent enough to send X amount of pressure one way and Y amount of pressure the other way. So what happens is that the higher pressure, which is feeding the north leg of the pipe, will also feed the south leg of the pipe. So instead of us requiring 0.606, we're getting 0.798 coming the south leg. Okay, so at that point, because we've got more pressure down there, and to get more pressure in a pipe, you increase the amount of volume of water in that pipe, so it squeezes more in. And when you're squeezing more water in, when the heads go off, more water comes out. So more pressure equals more flow. Okay, so what we need to do is work out what the actual flow is coming down this leg. Therefore, flow correction. Okay, so the equation for that is, so Q true, which is the correct flow, true flow, equals the high pressure divided by the low pressure. You square root that, and then you times it by the low flow. Okay, and when we square root the high pressure and low pressure, we get a ratio, and it's that ratio that we then times by the lower flow. So if we look at it here, P1, P2, Q2, so it would be 0.798 divided by 0.606, and then we times that by 152.08. Therefore, my true flow going down the south leg is 174.51 litres per minute. And if we wanted to work out what the actual flow going down both legs were, we would add the flow from the north leg, add the flow from the south leg together, which gives us 327.9 litres per minute. And the pressure required at that point there is the higher flow, is 0.798. Okay, so this pressure required at this point here to feed the 6 heads operating at the required density would be 327.9 litres per minute at 0.798 bar. If we take this further and then we work out where do we get these flows and pressures from? So here's where we get them from. And this is what you need to do when you do your hand calculation. Okay, so bear with me, we'll try and take our time with this. Right, so first thing we want to do is take the furthest away head from the water supply here. Okay, so point A, what we'll do is the area that head is covering is 7.22. So what we're saying here is that the required flow from that head is density times area. So we only need 36.1 litres per minute. And if we use the pressure with the flow of 36.1 with a K factor of 18 square it, what we're saying is at that point here, at this head here, to achieve the density over that area, we only need 0.2 of a bar. However, we all know that the minimum pressure at ordinary hazard heads is 0.35. So we can't use that. So we need to work out the flow through this head and at minimum pressure. So we're going to use the Q as the K factor times the square root of P. So using the 0.35 bar, the flow through this head is 47.3 litres per minute. So it's 80 times the square root of 0.35. Okay. Right, so at this point here, what we want to do is work out the pressure loss down here. So we're going to use the Hayes and Williams formula here. Okay, and remember, we need the pressure loss equals the K factor times the flow to the power of 1.85 times L. So the K factor we would get from TB227 table 2, it's medium quality, 25 pipe, and that works out at 8.66 times 10 to the minus 6. Now the flow through this pipe is the flow from head A. Okay, so we've got the K factor, we've got the flow, and the length of that pipe is marked down in the drawing at 3.010. It has to be in meters. So when we work all that out, we work out that we're getting the pressure loss down this pipe of 0.033 bars. At this point here, we want to work out the flow from head B. Now, the actual pressure at head B is going to be the pressure required at head A plus the pressure loss through the pipe A to B, because we only need the same pressure. We're only losing pressure down that pipe, so we need to add that pressure to that head. So the actual pressure at this head here is 0.35 plus 0.33, which gives me 0.383. When we work out the flow from that head, it is 80, which is a K factor, times the square root of the pressure. So the actual flow from head B is 49.5. Okay. Now to work out the pressure loss from pipework B to C, what we need to do is we need to work out what the actual flow going through that pipe is. And to work out the flow of what's going through that pipe, we add up the flow from head A and the flow from head B. And that tells me that the flow going down this pipe here is going to be 96.8. Now remember, we add the flows as we go back, and the pressure slightly increases as we go back. The pressure increase is called hydraulic gradient. Okay, you've heard me talk about that before during the courses. So 96.8 from B to C, and basically, if we take the Hayes and Williams formula, we get the K factor from table TB227, table 2, the flow, which we get from the two heads, and the length of pipe is 2.875. So when we put all that together and we do that calculation, we find that the pressure loss down B to C is 0.117 bars. Okay? So just keep using the process and you should get your way through it. Now, when it comes to the flow from head C, what we need to do is add the head pressure at B plus the pressure loss. And if we add that to that, we end up with 0.5 bars. So it's 80, which is a K factor of the head, times the square root of 0.5, gives me a flow from that head of 56.6. Okay. Now, last but not least, we've got the pipe from C to D. Okay. So what we've got the flow, which is not, we've got the flow here, which is the flow from head A, B, and C, which is 153.4. Okay. So if we use the Hayes and Williams formula, we get the K factor from table TB227, table 2. We've got the flow, which is the flow from the three heads, and the length of the pipe is 1940 plus 3290, or 1.94 plus 3.29 plus 0.985 plus 0.655, including the equivalent length of 1 to 3 32 elbows, which we get from table 23. Okay, we add all that up, and what we're saying here is that the actual length of pipe, including the elbow equivalent lengths, is 11.97 meters. Okay, now we don't need to do calculation for every single pipe. So basically, like we talked before, when you're calculating a pipe with bends and elbows, we're making it one big straight length of pipe. Because it's the same size of pipe, we don't need to do a separate calculation. We can work that out. Okay, so basically it'd be 2.25 times 10 to the minus 6 times 153.4, which is the flow from the three heads, to the power 1.85 times 11.97, which is the length of pipe, including the bends. So the pressure loss through this pipe from C to D is going to be 0.298. So from the north leg, okay, the flow of 153.4 does not increase here because we're not increasing head flows. However, the pressure required would be the pressure at the last head on that leg, plus the pressure loss from the last leg back to the point of pressure, which is D here. So the north leg, we need 153.4 at 0.798 bars. So that's the north leg. We then need to do the same for the south leg, and it should be slightly easier. Okay, so if we come to the south leg, we work out what the flow from head E is, and we know it's going to be 0.35, there's 47.3. Okay. We then work out the pressure loss from E to F. So it's going to be the flow, which is here, the K factor, which we get from TB227, table 2, and the length of the pipe, which is 2.565. So the pressure loss down E to F is 0.028 bars. Add 0.028 bars to 0.35. So the pressure at head F is 0.378. Okay. So if we do the calculation, K factor times the square root of the pressure, that means that the flow from head F is 49.2. And you can see the difference right away. Because we've got a shorter pipe, the flow is less. Okay. So that's why you've got a less flow. You've got less pipe, less pressure build up, less flow. So to work out the pressure loss down F to G, we add up the two flows from E to F, which gives me 96.48. K factor comes from TB227 table 2, and the length of the pipe is 2.565 meters. Okay. So if we do that, 8.66 times 10 to the minus 6 times the flow of 96.5, 96.5, I've rounded it up slightly, to the power 1.85 gives me a pressure loss of 0.104. Okay, so the pressure at head G is the pressure at head F plus the pressure loss. So the pressure at head G is 0.483. You can see the difference in the head pressures. So the flow from that head, okay, the flow from that head is 55.6. Right, so the last piece of pipe is from G to D. So to do that, what we need to do is we take the flows from each head, E, F, and G, which gives me 152.8. You can see there's a slight difference in flow. And then we take the pressure at head G. Sorry, we've got the flow, we've got the K factor from TB227, table 2, and we've got the length, which is 1305 plus 655 and an elbow. So the pressure loss down E to D is 0.123. Okay. We then need to work out what the flow and pressures are for the south leg. Now on the south leg, it's 152.08 and it's 0.606 bar. If we add up the last pressure at head G and 0.123, that's what we get. Alrighty. Now we're not finished there. Because we've got a higher pressure above and a lower pressure below, basically we're going to have to do a flow correction calculation. Now the best thing to do in a situation like that is to reduce this 32mm pipe to 25. And what that'll do is it'll increase the pressure loss and it'll bring your pressure requirement from here to here roughly the same. Okay. Now, if we do that, it means we're going to have less flow going down the south leg. Okay. So it's going to minimise your hydraulic gradient. Alrighty. Anyway, you get that over time. We're just playing about with calculations and stuff like that. Alrighty. So the flow correction is going to be the square root of the high pressure divided by the low pressure times the low flow. Now we've done this already, so we know that the flow actually coming down this leg is going to be 174.6. We've done that in the previous slide. Okay, now here's the thing. What we want to do is we want to work out what the actual flow from head G, F, and E are. Now it's pretty much what we've done working from E to G, but we're going to work it back the way. Okay, so we know this piece of pipe here has got a correct flow of 174.6 going through it. So if we use the Hazen-Williams formula to work out what the pressure loss through that pipe is, we'll find that the pressure loss through that pipe is 0.16. The K factor from TB227, table 2, we know the length of the pipe, with including the elbow plus the flow. Okay, so if we do that, what we're going to have is 0.16. So at head G, okay, we know that at point D, we're going to have 0.798 bars, okay? And so if we take the pressure loss through this pipe away from 0.798 bars, that then gives me a pressure, an actual pressure at head G of 0.629. And if we do a calculation of the actual flow through that head, what it does is it gives me 63.4 litres per minute, which is quite a bit difference from 55.6. Okay. Now we then need to work out the pressure loss through pipe G to F. Okay. So the pressure loss through G to F, we're going to use the flow. And now to get the flow through this pipe, we take the flow from D to G, and then we take away the flow from this head because it's discharging the water. So it's 174 minus 63.4. So the actual flow going through pipe G to F is only 111.2. We know the K factor of the pipe from the tables, TB227, table 2. We know the flow, we've just worked it out. And we also know the length at 2.565. So the pressure loss down that pipe is 0.135 bars. Okay. Now to work out the flow from head F, it is the pressure at head G minus the pressure loss down the pipe G to F. So the actual pressure at head F is 0.494, which is quite a bit difference from what we had originally. And then if we work out the flow from that head using K, which is 80, times the square root of 0.494, that gives me a flow of 56.2, actual flow with the true flow. Okay. Moving on to head E. So basically, if we move on to head E, okay, what we'll do is we take the flow from G to F, which is 111.2, minus the discharge flow from head F, the actual discharge flow from head F, which is 56.2. So the actual flow coming down this pipe is 55 litres per minute. Using the K factor from table TB227, table 2, the flow of 55 and the length of 2.565, we'll find that the pressure loss is 0.037. Okay, now we take the pressure loss off of the pressure, the actual pressure at head F, which is 0.494. So that gives me an actual pressure at head E of 0.457, which is 54 litres per minute, 56 and 63. And you can see the difference. So because we've got more pressure going down the south leg because of the true flow, we're actually getting more water out the heads E, F, and G. Now, if you wanted to work out the density, the actual density from E, F, G, what you would do is you would take the area of that head and you divide it by, you divide the flow by the area of that head, and that will give you the density coming out of that head. And you'll find that the density, as it comes back from head A, increases. Okay. Right, anyway, so if we jump back, we want to work out what the pressure loss is coming down from D to WS. Now, what we've got to do is we've got to add the flow from the north leg and the true flow from the south leg. So if we add 153.4 plus the true flow of 174.6, the actual true flow going down head pipe D to WS is 328.1. Now we know the K factor because we can get it from the table. So that's TB227 table 2. You've got the flow. And you've also got the length at 2.095. Okay. So when we work that out, what we'll find is that the actual pressure loss down this pipe with the true flow from above and down is 0.03. Okay. Now, what we're saying here is to get the actual flow and pressure from the water supply here, we've added the flow from the north and the true flow from the south at 328, so that's not going to change. However, the pressure itself is the higher pressure of the two, which is 0.798 plus the pressure loss down that pipe. So therefore, the pressure and flow at this point here is 328.01 at 0.801 bar. Okay. Right, hopefully that's helpful, guys. Yeah, hopefully that's helpful. Okay.